I want to talk about hybrid quantum classical neural networks and their application to the field of site reliability engineering. As you all know, like the quantum computing field is picking up. Google has launched a new chip Willow, and so has Amazon recently, and they have passed the benchmarks. But to make use of them practically now, for especially the emergence of AI and machine learning, we are looking into the hybrid approach of hybrid quantum and classical neural networks. I have briefly split the agenda into hybrid quantum classical neural networks. I'll say HQCN, and it's been very long to pronounce. The challenges that are in this approach, the practical applications, and the SRE aspect of it. Okay. So the left column talks about the quantum advantages. The quantum computing takes advantage of the quantum principles of physics, which is superposition. Superposition is the ability of data to be in all the possible states at once before it's being observed. If you take in binary, we call it a 0 or 1. It could be a 0 or 1, both 0 and 1, before it is being observed. So this rises to the concept of parallel universes and the ability to solve the problem parallelly in parallel universes. And the quantum entanglement is the ability of one qubit. Qubit is the basic unit of like a bit of quantum computers. Ability of one qubit to affect the other to the same state, irrespective of their distance. This adds tremendous power to quantum computing. And the modeling of quantum states using Hilbert spaces provides unprecedented power to solve problems. And as the classical strengths, it's well established, like what ChatGPT is using, or any other Anthropic or any other neural network is using. They're using regular binary computer, not regular, but established high GPU classical computers. When you fuse both of them, so basically you're using a combination of classical. You basically provide the problem in classical, which is encoded into quantum state, and you return the result back in classical after validation. That provides unprecedented problem solving capabilities. Now enters the parameterized quantum circuits with their quantum algorithms that incorporate tunable parameters within quantum gates, enabling optimization of tasks. As you can see in this graphic, the presentation. So there is a feature mapping part below, which basically maps the classical part features to the quantum states. And the quantum parameters are tunable elements within the quantum circuits that enable optimization for specific tasks such as quantum machine learning. Classical gradient-based techniques, the one that is used in the last piece, classical optimization, are tunable elements within quantum circuits that enable optimization for specific tasks. And techniques like gradient descent are foundational, which iteratively adjust parameters to minimize the cost function. I think the slide is slightly bigger. So this slide compares the HQCNNs with the traditional classical neural networks, and you can see that consistently outperform the classical computers and the neural network approach, despite having noisy data, and we still have stability issues with qubits, which is yet to be resolved, especially in complex high-dimensional tasks like medical diagnostics or drug discovery. So it's got a huge implication on, think of it like this: if you can find the vaccine for cure COVID within hours rather than months, see the impact it can have on the number of lives that we could save. So there is a potential of this approach. Okay, I'm going to share. So now comes, how do we train quantum circuits, deep quantum circuits? First is the circuit initialization, where you structure quantum layers with appropriate gate operations, and parameter optimization, applying grade descent and base methods, Next is error mitigation. And finally, you evaluate the model. Basically, you take a known benchmark and you run it both in the classical as well as on the hybrid quantum computer, and then confirm that the quantum works or it is within the benchmark of the classical computers for accuracy. Okay. So the advantages of high dimensional computation, I know this as in the slide, it speaks up like the things that we talked about. It's made up of qubits and it has got the typical quantum advantages of superposition and entanglement and quantum parallelism. So basically it is almost like having parallel universes to solve a problem. You can think about the consequence of that thought. And especially on high dimensional data, which requires basically a lot of possible ways to look into the solution. They are very greatly efficient, especially compared to the classical representation. Efficient optimization, quantum algorithms, vast solution landscapes. Like assume you want to come up with a financial modeling and you want to say what happens when I do it on this day. If you want to take the 365 days of a year and calculate the interest and the subsequent pension that you will receive after 60 years, the classical computer would struggle, but whereas the quantum can easily model that in just a jiffy. The dimensionality advantage, hybrid architectures seamlessly integrate both quantum and classical datasets. Basically, it maintains the regular computing advantages of practical use of it, and also the quantum advantages, which is the ability of it to solve problems with high dimensional spaces. Now, let's look at some of the applications. It's very exciting. Like whatever we talked till now, it's more like a theory, but this is practical, right? Especially in medical diagnostics, like if to read an MRI scan or combining multiple data, multiple scans together and deriving conclusions out of it, which can be critical for the patient's diagnosis. So this offers unparalleled potential. Drug discovery, as I mentioned, like we are doing a little bit, like COVID was done pretty fast, but quantum can do it within no time, almost like minutes or day or hours, which basically gives us the ability to think about novel drugs, which can completely change the life of people and cure diseases. Yeah, the other frontier is the personalized medicine. You have multiple data sets, right? You have the clinical data where you go to a GP or have your medical test, and the environment that you live in, your predisposition, your genomic data. The HQNNs, they can combine all of these and produce very personalized medicine, like the one that perfectly works for you, depending on all the parameters, which may not be so easy to do right now. As I talked, the potential applications are in financial modeling. Give me 1 second. Trying to move this. Okay. Financial modeling. Then again, the supply chain logistics. It's like an operational research problem. You have limited resources and what is the best way for the cost being optimized or the faster delivery for critical medical emergencies. It's a very good area to work on supply chain logistics. And it can help itself. It can design efficient quantum and classical circuit layouts, which can make it even more efficient. And also one benchmark is like they have demonstrated that for 200 plus training iterations, the variance is only between 2%, which is pretty high accuracy, stability. Okay. The way we train a quantum hybrid HQ CNNs is we have to first have the dataset, a classical dataset, and then we have to prepare it into a format that's digestible by the quantum computers, like amplitude. So basically, you convert that into a voltage or direction, like a phase envelope, and then encoding the feature maps to preserve the critical relationships. Okay. And next, like executed forward pass is they do one iteration, move forward to perform complex transformations on the encoded data. And then the data is sent back to classical back propagation is enabling efficient organization across the quantum and class. So quantum has computed, the data is available in the quantum format. We need to pass it on to the classical format. And the hybrid optimization, systematically define parameters to iterative quantum classical feedback loops. So basically, the earlier ones that we gradient descent, we saw that, right? So you keep on doing iteratively to optimize the hybrid system. It's not very straightforward. There are a lot of challenges. It's in much still in the state of infancy, but it's quite an interesting problem, and eventually we'll get there. So one is quantum decoherence, like the challenges. I mean, despite we say that the qubits we have made it much better than what it was, but still they suffer from instability, and the error mitigation techniques are still work in progress. And scalability is one issue, and barren plateaus, like when the is a critical training problem in quantum machine learning QML, specifically in training PQCs, parameterized quantum circuits using gradient-based methods. So basically, when the quantum circuit becomes deeper and deeper, the the gradient vanishes. So that is a problem. That's a common problem or a problem that's studied deeply, barren plateaus. And the classical quantum interface, the data transfer between our classical systems and quantum, they create bottlenecks, and hybrid algorithms must minimize this overhead. Okay. So the future outlook as Google, Amazon, Microsoft, everyone is working towards, even NVIDIA, they're working towards more quantum computing chips with more qubits, coherence, and gate fidelity. And on the software side, the algorithms are also improving. Novel hybrid architectures are created. And the other thing is, we are talking, this is now happening in labs, in some universities, or in some like top companies' labs or R&D divisions. But well, it has to become a widespread industry adoption. And the quantum enhanced machine learning has to become a standard. Yeah, but they will surely revolutionize the computational approach. And when this matures, solving the problems that we could not solve earlier, or could not even think about earlier. Now, the relevance of, we discussed about quantum, we discussed about classical, and how HQCNNs, a hybrid quantum computing neural network model, like computers, how they work and how they can help us in drug discovery and personalized medicine, financial modeling. We talked about all that. Now, what are the problems from a SRE perspective? One is the handoffs is a point of failure, and because the movement of data from classical to quantum, so that's a point of failure. So we, from a SRE perspective, systems SREs have to design robust interfaces and ensure that there's no data loss or data transformation. The other important piece I want to talk about is the observability. Okay, now if you have a cloud computing system, you have a way to observe it. So how do you observe a quantum state? How do you observe quantum noise? How do you observe quantum decoherence? And how do you observe latency? How do you know the model is performing well? Is it not drifting away? How do you know all those things? So observability is a very important part of it. And error mitigation strategies, right? If there is an error during a handoff or initial data encoding, how do you come up with ways to mitigate the errors? Okay. And scalability is another problem. And deploying, okay, suppose there is a new model that's getting deployed. So how do you deploy it into the quantum space? Do we need any special orchestration techniques, containerization strategies, where the SREs have to come up with new models and something that they have not thought about till now? And SREs who are supporting that, they have to ensure that they can deliver a level of repeatability, low drift, and even when the system is loaded with a heavy model or a low test parallelly, it should not drift, and it produces the same consistent performance even during load. SRE must manage the handoffs, error mitigation, this we talked about earlier, and monitoring and observability and scalability, right? Like how do you, suppose you want more clusters, how do you scale on demand? Can you do it within a few milliseconds so that there is no loss in the performance? Those kind of things are very critical for an SRE. And I put together a set of references for you, the Qiskit one from IBM and the parameterized quantum circuits, and or how to build reliability by IBM. And practical use recently, UT Austin, they came up with a way to test whether the numbers that are generated by a quantum computer is really random using a classical computer. I put across some references. You'll like it, and you learn something out of it. Yeah, that's all I have. Hope you like it. Thank you very much.